Taara, revolutionizing internet connectivity with free space optical tech. Picture this. Billions of people around the globe are still stuck without reliable internet access. And it's not just about wiring up remote homes anymore. It's the tricky stretches between cities and over rugged landscapes that's holding everything back. That's the heart of the middle mile problem, and it's a challenge that's evolved dramatically since the early days of the web. But here's where Taara comes in, offering a fresh take on connecting the world with laser-based tech that's as innovative as it is practical. Stick around because we're about to dive into how this works, the hurdles they've overcome, and why it might just change how we think about global connectivity. Fast forward from 2 decades ago, when tech enthusiasts were all about tackling the last mile issue, getting internet signals from the main lines right to your doorstep or down country lanes. Today, the real roadblock to broader internet access lies in the middle mile, navigating through urban areas, crossing vast rivers, or scaling mountains where laying traditional fiber optic cables is a massive headache. Enter Taara, a company spun off from X, the innovation hub once part of Google, which is pushing a straightforward alternative, free space optical communication, using infrared lasers in the C-band. This approach beams data through the air, promising speeds up to 20 gigabits per second over distances as far as 20 kilometers. To put that in perspective, it's like sending high-definition video streams without any physical wires, making it a game-changer for areas where digging trenches isn't feasible. Now, you might be wondering, what exactly is free space optical communication? Think of it as using invisible light beams to carry data, much like how fiber optics work, but without the need for buried cables. Taara's system relies on eye-safe lasers that shoot infrared light between 2 points that have a clear line of sight. This technology isn't entirely new. C-band communications have been around for decades, but Taara has refined it with modern tweaks in optics, electronics, and software to make it more reliable and efficient. For beginners, imagine shining a flashlight across a field to send a message. Now scale that up with precise lasers that can handle enormous data loads, and you've got the basic idea. And this is the part most people miss. While the hardware looks simple, it's the smart algorithms that keep the beam locked on target, even with a bit of environmental interference. But here's where it gets controversial. Why haven't other companies jumped on this bandwagon earlier, given that the underlying tech isn't revolutionary? Some might argue that past failures in similar projects, like Google's own ventures, show it's not as foolproof as it sounds. Taara's CEO, Mahesh Krishnaswamy, shared insights in a chat with IEEE Spectrum, highlighting how their approach builds on lessons from projects like Google Fiber and Project Loon. Krishnaswamy explained that Taara started as an X-development project about 7 years ago and has now become an independent entity. Their goal? To bridge the digital divide by providing high-speed connections where traditional methods fall short. He noted that nearly 3 billion people lack internet access, and even those connected often deal with slow speeds or high costs. By using lasers to link points across difficult terrain, Taara helps reduce these inequalities. Take, for example, their deployment across the Congo River, separating Brazzaville and Kinshasa. This river is not only one of the deepest and fastest flowing in the world, but also a natural barrier that's made laying underwater cables nearly impossible. Instead of routing around it for hundreds of kilometers, Taara's technology created a direct link, slashing bandwidth costs and bringing parity to both sides. This kind of application shows how free space optics can offer quick, cost-effective solutions, but it also raises questions. Is relying on line-of-sight technology sustainable in a world with unpredictable weather and wildlife? Krishnaswamy admits that weather is a big challenge. Fog, in particular, can scatter the laser beams and disrupt signals. To counter this, Taara uses predictive tools to assess deployment sites and ensures that as long as visibility is good, the connection holds. They even incorporate mesh networking ideas for rerouting data if needed, making the system more resilient. Shifting gears to what makes Taara's tech feasible now, when it wasn't as effective a decade ago, Krishnaswamy points to advancements in components like better optics, refined electronics, and sophisticated software algorithms for aiming and tracking the lasers. Their current product, Taara Lightbridge, is about the size of a traffic light and can handle 20 gigabits per second, bidirectionally over up to 20 kilometers. It's already operational in over a dozen countries, proving its worth in real-world scenarios. But Taara isn't stopping there. They're working on a major upgrade, a compact photonics chip that's no bigger than a fingernail. This prototype can already transmit data at tens of gigabits per second over short distances, both indoors and out, and it's set to launch by the end of 2026. This chip could not only extend ranges and boost speeds, but also shrink the gap to the last mile, potentially connecting individual homes more directly. To clarify the middle mile versus last mile distinction for those new to this, think of the middle mile as the backbone routes that carry data from major hubs to local distribution points, often spanning several kilometers through challenging areas. The last mile is the final stretch to end users, which could be as short as a few dozen meters in urban settings. Taara's tech primarily targets that middle segment, but with future innovations, it might blur the lines even more. Krishnaswamy, drawing from his experience at Project Loon, where balloons relayed signals in the sky, adapted those airborne concepts to ground-based stations for faster, more stable connections. One of the trickier aspects is maintaining a precise aim over long distances. Imagine trying to hit a target 20 kilometers away with a laser pointer while monkeys are shaking your setup. That's a real issue Taara faced in India. They solved it by integrating gyroscopes and accelerometers to keep the beam steady, along with cameras for real-time adjustments. This secret sauce in pointing and tracking is what sets them apart, but it also sparks debate. Can such systems truly handle all the variables nature throws at them? Or are there scenarios where fiber optics would still be superior? Looking ahead, Taara's ambitions include making their technology more manufacturable and versatile. Krishnaswamy, with his background at Apple, is applying lessons in scalable production to push boundaries. Beyond internet connectivity, this tech could revolutionize other fields, like enabling ultra-fast communication in self-driving cars or enhancing LiDAR systems for better environmental sensing. It's an exciting vision, but it invites controversy. Some experts might argue that free space optics will never fully replace fiber due to its vulnerability to weather, while others see it as a complementary solution that could accelerate global access. As we wrap this up, think about this. In a world racing towards more connected futures, is laser-based communication the key to unlocking untapped potential? Or does it carry risks that could leave communities in the dark during bad weather? We'd love to hear your thoughts. Do you believe Taara's approach could bridge the digital divide more effectively than traditional methods? Or are there limitations that make it less appealing? Jump into the comments and share your take. Let's spark a conversation on how we can make the internet truly universal.